So you keep on doing this. And then, let me just show you what happens in a cartoon diagram. Suppose that your J1, let me not use red here. Suppose that your J1 was 2, J2 is 1. Then what is J? J is going to be J1 plus J2, right? So it's going to be 3. So the highest, angular momentum that we are going to get, okay, let me use a red color for that. That is going to give me J, right? And then I'm going to apply to it, a lowering operator. And when I apply to a lowering operator, I get, sorry, I'm just going to make a huge mess, but I'll try not to. So when I apply lowering operator on this, I get J minus 1. And then if I apply another lowering operator, I'm going to, so what I'm going to do is the following, is that okay. So this is going to be something like this. Okay, let me count. I need 1, 2, 3. 1, 2, 3. Good. So let me draw the picture and then I can describe, how to do this rather than. So the line that I've drawn is going to contain all the states in the multiplet, okay? Okay. Let's see. Okay, yeah. Let's try this. So we have, that's going to be the highest weight state, and this is going to be the lowest weight state. And as I apply the lowering operator, I'm going to get 1 by 1. I'm going to get these states, okay? So I assume that J1 was 2. Then how many dimension is going to be this multiplet? If J1 is 1, then the D dimension of that multiplet, so say 2. Then the dimension of that multiplet is going to be how much? 2J plus 1, right?
Yes, sir.
So 5. So do I yeah, sorry. This is J. J is 3. Then if J is 3, then sorry, the total J is 3. Sorry for getting confused. J is 3, then the dimension is going to be 7, right? And do I have 7 points? States 1, 2, 3, 4, 5, 6, 7. Yeah. So as I apply lowering operator, this thing is going to go down like this. Okay. You might say, okay, why did I draw it in such a weird way? You will see very soon. So this is, the highest weight state. But as I applied my lowering operator, I went to jj minus 1, right? The next state. But we know that, there's another state with the same jz eigenvalue. And that state is going to be, I'm going to draw here, and that state will be the highest weight state of another multiplet. Okay. And that multiplet is going to have j minus 1, j minus 1. And as I apply lowering operator on this, I will have, let me draw another one. Yeah. So as I apply lowering operator on this, I'm going to get other states like this. And just by doing the lowering operator, you're going to find out what this state is. Like, I'm just going to circle this state and this state. Remember that when we made this state, we knew what this state was. And because we knew the linear combination of this state, we could take a different linear combination to make this state, right? Do you remember that?
Yes, sir.
So similarly, we are assuming that we have made all these states, right? So next time, what we do know is that we know this linear combination automatically. Because we started here, we applied a lowering operator, we automatically know what this state is. We don't have to work. These two states are given. So, but then what I do is that I'm going to, given the information I have about this state and this state, I can easily create the state here, which will be orthogonal to both this state and this state. Okay. And this state is going to be j minus 2, j minus 2. It'll be a maximal weight state for a new multiplet, okay? And that new multiplet, sorry. Yeah. And that new multiplet is going to have 3 states. And that is all we have, because remember that our conjecture was that the highest value will be j1 plus j2, which in this case is 3. And the lowest value will be j1 minus j2, which in this case is 1. And if you have 1, how many dimensions do you have? The dimension is 3, right? So we see that we have reached a 3-dimensional Hilbert space. So these are the different Hilbert spaces completely orthogonal to each other that we can create out of these two spins, okay? So, if I have two spins, two angular momentum, one with J1 equals to 2 and J2 equals to 1, then when they're parallel, they will form a 7-dimensional Hilbert space where the total angular momentum is 3. If they're not exactly parallel, they will form a angular momentum where the Hilbert space, where the total angular momentum is, 2, and the dimension of the Hilbert space will be 5. If they're anti-parallel, then they will form a system whose total angular momentum is 1, and there are 3 states here. Okay. Now what I'm going to show is that they all add up to the right thing. Okay, so what do I mean by that? Because I told you that these were conjectures, but recall that our original system consisted of two spins, two angular momenta whose j squared eigenvalues were j1 and j2, right? So the first one was 2j1 plus 1 dimensional, and the second one was 2j2 plus 1 dimensional, right? So the total number of states, in that combined space must be the product of these two numbers, right? Because they're independent objects. Do you agree?
Yes, sir.
Yeah. And now what we have done here, we have reorganized them in, so this is some big product Hilbert space, but that Hilbert space breaks up into orthogonal, subspaces, which are given by these spaces. So if I add these spaces, add the number of dimensions of these spaces, they should add up to this number, right?
Mm-hmm.
And that would be the proof that our conjectures were correct, because otherwise we would have missed something. So let's do that. Let's prove that. So we took J, that or let's call it, say, total. Okay, let's call it total. Let's call it total. Total angular momentum and number of states in that Hilbert space. Okay, so first we took them to be J1 plus J2, right? So then the number of states here is 2 J1 plus J2 minus 1. Sorry, plus 1. And then we reduced it by 1. We took J1, J2, and then reduced by 1. And that Hilbert space, that multiplet will have 2 J1 plus J2 minus 2 minus 1, right? Because 2 times this minus 1 is this thing. So this is all easy. And we go down to the most anti-parallel case where it's going to be the lowest, and that's going to be J1 minus J2. Now, how many states are there for this guy? To do this, let me rewrite this in a different way. Let me rewrite this in this form. So to come from here down to here, how many steps do I have to take? That's what I want to find out. So that is going to be J1 plus J2 minus 2 J2. So to get to the bottom of this list of multiplet, I have to go 2J steps. And that will also give me, what numbers do I expect here? Well, the number that I should get, because I know this thing, so I can get the dimension very easily, 2 J1 plus J2 minus 2 times 2 J2. Okay?
Wouldn't there be a plus 1 or something?
Right. So if let me see. Okay. If I do this, if I say 2 J1 plus J2 minus 2 J2 plus 1, then I will get to J1 plus J2 minus 2 times 2 J2 plus 1. You're right. So I should have a I should have a plus 1 here, right? Yeah. I should have a plus 1 here, and I should probably also have a plus 1 here, right? Now, hey, what do you think? That should be a plus 1, right?
I think so, yes.
Yeah. Okay. So, right. So now what we have here an arithmetic series. Okay. So an arithmetic series. Well, actually, no. One of the part of it is arithmetic. All these guys are the same, right? All these guys are the same. And how many? So if I add this up, if I add all of this up, what do I get? It's a few lines of algebra, and I will. Well, I can try to do this. Okay, let's try to do this. I may make a mistake, but that's fine. So how many terms are here? There are 2j plus 1 terms, right? 2j2 plus 1 terms. 2j2 plus 1 terms, right? And that'll be that many of these guys. So this will be multiplying 2 times j1 plus j2. That takes care of the first term. And then what do I get? Then I should get, there is 4 j2 here, right? So hang on. Okay. 2j, yeah, okay. Okay, so then let's count these ones. Okay, so there's going to be ones in all the one. So there's going to be plus 2j2 plus 1, right? Do you agree? I'm just counting the number of ones for in each Hilbert space, in each dimension. And there are 2j plus 1 terms, right?
Yes, sir.
Okay. You guys have to help me because I'm not sure if this is going to work out because I didn't really work out the whole thing in my notes. Okay. Anyway, but if you don't get it, we don't get it. That's fine. And then we are going to get these terms, and which come down to this thing, which is an arithmetic series. Okay. And here, what we do is that we have a minus 2, and the first term is 0, and the second term is 1, third term is 2, ... 2j2. Okay. So now, if I look at the the expression for the sum of arithmetic series, what is it? It's basically telling me how many terms there are. Well, it's got I have so we can ignore the first guy, of course. Then we have 2j2 terms, right? Divided by 2 times the first term, sorry, the difference, right? Is the difference, or do you remember the Sn is equal to n by 2, and then what?
N times 1, n plus 1.
N plus 1?
Yeah, I think that's...
No. There's an A or something like this, right? Okay, let me just look that up, okay? Let me look that up. Okay, some formula. I always forget this. Yeah, I found it. Yeah. is S of n is equal to n by 2, and then 2a plus n minus 1 d. Okay? So here n is going to be 2j2. And what is a? A is 1, right? So we get 2a. And then n is again 2j2. So 2j2 minus 1. D is 1, right? Okay? So this is going to be half is going to give me, and then what should I, okay, and then I get
J2 times 2J2 plus 1.
Yeah. So
So this was a
Two-
special case, so I think the n times n plus 1 by 2 formula would hold.
yeah, anyway, so this is 2j2 plus 2j2 squared, right? Minus j2. So we have 2j2 squared plus j2, right? So which is j2 times 2j2 plus 1. Did I make a mistake? Guys, did I make a mistake? Please check.
It matched with mine, so maybe.
Okay, let's make mistakes, but let me then add everything up. Okay, so we are going to add everything up, and I have a bad feeling that this is not going to work out, but that's fine. This is okay. So this is going to be 2j2 plus 1. There's a factor of 2. j1 plus j2 plus 2j2 plus 1, and then we are going to have minus j2 to j2 plus 1, right? So this and this আমরা common নিতে পারি, right? And this one too, right? So we get 2j2 plus 1, and then I have 2j1 plus 2 j2 plus 1 minus j2, right? So I think I'm missing a factor of 2 somewhere. So probably there should be a factor of 2 here. And yeah, there is a factor of 2 here, see? Which I forgot in the sum, so there should be a 2 here, yeah. So if there's a 2 here, then this thing will cancel this thing, and we will have 2j2 plus 1, 2j1 plus 1, which is exactly this number, okay? So we have not missed anything, that our two angular momenta breaks up into this beautiful orthogonal sets of Hilbert spaces, and if I sum all the dimension of all the Hilbert spaces, that is equal to the product of the dimension of the Hilbert spaces of the component angular momenta. Okay, all right. So okay, any questions? This was a bit of a tough slog, but I'm very happy that we went through it. Any questions?
So far, no, but I'll have to go to the algebra again.
Yeah, you have to go through the algebra.
Yeah.
It's like every time I have to teach Clebsch-Gordan coefficients, it's always has to do all this stuff.
Yeah, this one is a tough one to solve.
But it's easy. It's conceptually it's a very beautiful thing. It's a very beautiful thing. Okay, let me say a few words. The coefficients, of linear combination are known as I'm always making Clebsch-Gordan coefficients. And what do they mean? They give you the amplitude for the correlation of the two component angular momentum. So what does this mean? So we are looking at some state, right? Psi. But suppose that we say, okay, I want to take the first angular momentum, say J1. I'm going to compute J1Z, J2Z. I'm going to compute what the correlation of these things. This is called a correlation function. Like, with the product, this from statistics. So the Clebsch-Gordan coefficient tell you what these things are. The square of them, rather. Okay.